Okay, good morning, everyone. So today we are exclusively going to look at problems, problem solving, specifically three examples, two for AC analysis and two for AC power. Well, three examples because the second example is regarding AC analysis, where we calculate the currents and voltages, and then we will calculate power. So two examples for AC analysis and two for AC power in all. So let me switch over to the notebook. And so in AC analysis, or more specifically sinusoidal steady state analysis, we saw how we can use complex numbers to solve for currents and voltages when there's an AC source present in the circuit, right? We represent the sources, whether it's a voltage source or a current source, the time varying as a function of time. So we can represent those sources as complex quantities known as phasors. And we do the same thing with components, specifically inductors and capacitors, which have reactance. That reactance is represented by the complex number J in electrical engineering. And then we can apply all the analysis techniques that we have learned in chapters 1 and 2 to solve for AC currents and voltages. So now let's look at a combined source as well as a component. So in this circuit, now we have about three examples, but four different problems to solve through. So I already have my annotations on there. We'll specifically talk about everything on how to solve the problems, how to derive, well, not derive, how to apply the equations that we have derived, and how to create phasor diagrams, and then the power quantities. So in the interest of saving time, I already have the annotations on there. So we have a circuit here that has three components, R, L, and C, right? R, L, and C. Now we already know that when you apply an AC source to a resistor, it behaves exactly the same way that it does for DC. There is no change, right? A resistor does not have any reactance. Reactance is only present in the inductor and the capacitor, right? Only in the inductor and the capacitor. So inductors and capacitors have reactance X, XC, and XL. And a pure resistance combined with the reactance is termed as impedance. Impedance, again, is a vector quantity. It's a complex representation. The pure number in the impedance represents the resistance, and the imaginary number in the impedance represents the reactance of the inductor and the capacitor. Again, remember, in circuit analysis, everything is theoretical. Everything is hypothetical, meaning all components, all quantities are ideal. So an ideal resistor does not have reactance. An ideal inductor and an ideal capacitor does not have any resistance. So if you ever see impedance with a real number and an imaginary number, the real number will always refer to resistance. The imaginary representation has always to do with inductance and capacitance. Okay, so if you're given a number, let's say 25 minus J50. If it's 25 minus J50, 25 represents the real portion of the impedance, which is the resistance, and J50 represents the reactance. Okay, so for example, if Z is 25 minus J50, this represents resistance, and the 50 represents reactance X. Now, to determine what kind of reactance or what kind of component is referring to, we look at the sign. Inductor has 90 degrees positive 90 degrees phase shift, plus 90. So if it is a positive, if it's a positive number, then this reactance is referring to an inductor. If it's a negative number, it's referring to a capacitor. Okay, so plus J indicates it is an inductor, minus J indicates it is a capacitor. Now, of course, if we have an inductor and a capacitor in a circuit, then you could combine that impedance and the result would be either a plus or a minus. So there would be no way to, there would be no way to predict what kind of loads, what kind of components comprise this total reactance. This assumes that there is only one component in there. Okay. And again, that depends on the problem, right? If the problem specifies that there is one single load, that you can safely assume there's only one capacitor in there. Another way of putting it or representing it would be to say that overall the impedance overall has a capacitive load, meaning there could be a inductor present in the circuit, but the capacitive impedance is high enough that it cancels out some portion of that inductance. So the reason I'm going over this is because there's a homework problem. In the homework problem, it simply tells you the value of Z, and it asks you the question whether the load is inductive or capacitive. Okay, so it gives you the voltage to solve for the power. So this is a way of determining whether it's inductive or capacitive load. Okay, any questions so far? Microphone is off. Wow. Okay, so as I was saying, when you have a circuit and you're trying to find for the voltage and current for an AC source, the first thing to do, my recommendation is always to draw the equivalent impedance diagram. And the equivalent impedance diagram simply means you replace every component with its impedance. Okay, and I call it the equivalent impedance diagram. Okay, it's not like a technical word, it's just something that I use when I teach. Okay, so you represent every single component with its impedance, and what it does is it reduces the circuit to something that is familiar, right? We've seen this in chapter 1 and 2. You have resistors in the circuit, whether it's series or parallel, and now you can apply any technique you want, any technique that we have learned in chapters 1 and 2, right? So R, of course, remains R. Inductor L is replaced with ZL. Capacitor is replaced with ZC. And now it's a simple circuit, not simple, but straightforward circuit analysis problem. And we can see that we have three impedances in series, right? We have three impedances in series. So the question asks, find the total current I of t, find the voltages VR, VC, and VL. Short, it's asking for voltages across all the three components, and it's asking for the total current in the circuit. If these were three resistors, what would you do? Combine all resistors together in series, right? Find Req, meaning one single equivalent resistor, apply Ohm's law, and find I. Once you find I, you apply Ohm's law again, because the same current I is flowing through each one of those components. So you apply apply Ohm's law to each one of these components, and you find the voltages. The other method is to apply voltage division, which in the AC form, it will still work, except all quantities are now vectors, meaning they're complex numbers. So the techniques, the process remains exactly the same, only the mathematical calculations are different. Okay, so as a first step, I always strongly recommend drawing the equivalent impedance diagram, and that, reduces the circuit to simple circuit analysis problems. So we have three impedances in series. We combine impedances the same way we combine resistors, and so ZEQ, the total equivalent impedance, is simply R plus ZL plus ZC. If they were in parallel, you would again combine them the same way that you would combine impedances in parallel. And the next example, I have exactly that. We'll have a component in series and then two components in parallel. So ZEQ is R plus ZL plus ZC. I already know R. I need to find ZL and ZC, which is here on the left. Okay. So the next step after drawing out the equivalent impedance diagram is to extract the other information. I compare the given information to me with the standard expression for a time varying signal. Since the source is V of t, I compare that V of t with the standard expression Vm cos omega t plus or minus theta, and I get Vm is 100, omega is 500, theta is 30 degrees. Okay. Now, if you have programmable calculators, you can have polar coordinates, you can have rectangular coordinates, you can combine them in any form you want. My calculator cannot do so. So I do manually, right? And so since I need to perform an addition, R plus ZL plus ZC, I need to add the numbers. So I will try to find ZL and ZC in rectangular coordinates. But later on, I might need to perform a multiplication or division. And so I also find the polar coordinates at the same time. So rectangular coordinates would be J omega L. Polar coordinates would be omega L with an angle of 90. Omega L is common in both. Rectangular coordinates, you simply add a plus J. Polar coordinates, you simply add positive 90 degrees as the phase angle. So you plug in omega and L. You get J 150 or 150 with an angle of 90 degrees. Units, of course, ohms. Make sense? Same thing with ZC. ZC, I do the same thing. I'll find it in rectangular coordinates. So minus J50. And in polar coordinates, 1 over omega c with an angle of minus 90. Again, current leads the voltage, meaning the voltage is lagging. If the voltage lags, it's a phase angle of minus 90. And so impedance for a capacitor will always have a phase angle of minus 90. So 1 over omega c, 1 over j omega c, or 1 over omega c with the angle of minus 90. And so I get minus J50 ohms and 50 with a angle of minus 90 ohms. Then find ZEQ, plug in R plus ZL plus ZC, plus ZC, and you get 100 plus J100. See the inductance, if you look at the ZEQ, it has a plus positive value, plus J100. So overall, the impedance has an inductive load, right? If you were to connect this load and present it to a utility company, the utility company would say, overall, you have an inductive load because it's plus J100. But that total that total load is comprised of an inductor as well as a capacitor. The capacitor cancels out some portion of that inductive load. I'll repeat, the capacitor is canceling out a little bit of that inductive load. Make sense? Inductive load reactance is 150, yet overall the ZEQ is only 100. It's because the capacitor is canceling it out. This is a very important concept because in the next section, which is power, AC power, we use it for power factor correction. Right? Reactive power for an inductor is positive, whereas for a capacitor, it's negative. And so, again, this is where it comes from. Okay, so ZEQ in rectangular coordinates is 100 plus J100. At the same time, I will convert it into polar coordinates. Because the next operation I need to perform is a division. I'm applying Ohm's law. V equals IR. Again, in AC analysis, Ohm's law is V equals IZ. Right? Everything else, I mean, everything remains the same, except it's now vector quantity. So total current I is Vs over Zeq. Perform the math, and I get the answer as 0.707 with a phase angle of -15. Now, the reason I converted to polar is because, again, to repeat the same thing, my calculator cannot do 100 with a phase angle of 30 divided by 100 plus J100. So I have to manually perform this mathematical division. Right? If you have a programmable calculator, you can take this directly, 100 plus J100, and plug it into this equation, and you would still get your answer. Does that make sense to everyone? Let's take a 10-second pause. Let me know if you have any questions. Any questions at all? Yes.
Are these just two different methods of VR? You can do IR now in software, but we can also do voltage division?
Yes. Yeah. We can apply both. So that's basically what I have up here for student practice. So I'll talk about that at the end. But so far, all we have done is we found the total equivalent impedance in the circuit. We applied Ohm's law, and we obtained our answer, 0.707. Now, from here, we have to perform the inverse phasor transform to get the time domain expression. Because the question asks us for I of t. If the question asks you for the quantity as a function of time, then your answer has to be as a function of time. Okay. So you cannot leave the answer in vector form. 0.707 with a phase angle of -15 can be written as 0.707 cos of omega t. Omega is 500. Remember, that does not change. Omega is 500. It does not change. And so only the magnitude of the current changes, which is 0.707, hence cos of 500t and a phase angle of -15. And overall units, amps. Now, here, it does not give you t, meaning as a function of time. So VR, VC, and VL is not given as a function of time. But when you have a representation like this in lowercase, it is asking you for the time varying signal. So even though it does not specifically state as a function of t, it is still asking you for the answer in the time domain. And that's why I've left it like there. So both, whether the t is present or not, and if it's not present, it's asking you for the time domain expression. Okay, time domain expression. Lowercase is asking for time domain expression. If it was phasor voltage or phasor current, it would be uppercase like this. Okay. So these would indicate they are asking for phasors. And the others are time domain expressions. So once we have I of t, we simply apply Ohm's law to each one of these quantities. VR would be I times R, VL is I times ZL, VC is I times ZC. You simply take I, multiply with the respective impedances, R, ZL, and ZC. And again, you need to be adept at entering these equations in your calculators. Without that, you would not be able to solve these. Again, I do it manually, meaning I multiply the magnitude separately and I add up the phase angles separately. So VR is 70.7, phase angle minus 15. VL is 106.08, phase angle plus 75. And VC is 35.35, phase angle minus 105. Okay. Those are the three values. And then I transform them directly into the time domain. Frequency still remains the same. It's 500 T, right? Frequency remains the same for all components. And I get my time domain answers, VR, VL, and VC. Make sense? Does the overall process make sense? Math, of course, is something that as an engineer, you would have to practice on your own. But the steps are already outlined here. All right, any questions? Any questions at all? Okay. Well, if I wanted to draw the phasor diagram, I would have my real axis and the imaginary axis. All I would need is the phase angle and the length of the vector. So the only thing you would need to do, we'll first plot VS. VS has an angle of 30 degrees. So I have a 30-degree angle right here, right? And I draw a vector. This is not to scale. So 30-degree angle, and I get VS. Then VR has a minus 15. Minus 15 goes in the opposite direction. Positive angle is in the counterclockwise direction. Negative is in the clockwise direction. So minus 15 vector and draw VR. I is the same, no phase difference, and so it's right here. Minus 105. Sorry, minus 15. And then VL up here and VC down here. VL and VC are phase shifted with respect to the current. The current's right here, very tiny in black ink. Okay. Plus 90 and minus 90 with respect to the current I. Because they're in series, they share the same current, and hence we can say that the inductor voltage and the capacitor voltage are exactly out of phase by 180 degrees. If the connection is something else, if they don't share the same current, this phase difference would not be 180. It would depend on the circuit connections. But because they share the same current, these two components, the inductor and the capacitor, are out of phase by 180 degrees. One is plus 90, the other one is minus 90. Does that make sense to everyone? And that's the phasor diagram. Now, as student practice, I want you to apply voltage division. Equations are already written up. All you'd have to do is plug in the values, right? VR, VL, VC is the voltage across each one of those components. You're applying a voltage to a series connection of components. So voltage division. Vs of t is divided across the resistor. It's divided across the inductor and the capacitor. So the same equations that we learned in chapter 2 will apply here. A fraction of the total supply voltage is dropped across each one of these components. So VR is the total supply voltage Vs times R over ZEQ. VL is ZL over ZEQ, and VC is ZC over ZEQ. So the equations are still the same. You just have to recognize the circuit and apply those equations, plug in the values, and then solve. So AC analysis is very similar to DC analysis, and that is because of the magic of the complex number or the imaginary number. All right, let's take 10 seconds. Questions? Yes.
Could you go down to the phasor diagram?
Yes. Let me remove this.
And if we were to do a phase diagram on a test, you wouldn't necessarily count the length most of
No,
the
No. Yeah. And it'll be a straightforward phasor diagram like this one, if at all. No KVL or anything like that. No. We leave that for the lab. All right, any other questions? Okay, so chapter 5 is then officially closed. I think there is a homework based on this that is still due today or tomorrow. Tomorrow, yeah. So most of it was already covered. So, and a lot of students have already finished it. But this last remaining problem, and that's why I extended that homework by another day. So now let's look at AC power. AC power is right here. Now we had all these equations and we looked at the power triangle. Right? We looked at the power triangle. It's a right angle triangle. The real power has to do with the resistance and it is lying on the x-axis, the real axis. And the reactive power is represented again by the imaginary number. So it lies on the imaginary axis. QL is always positive, 90 degrees up. QC is always negative, 90 degrees south or down on the negative imaginary axis. So it forms a right angle triangle. From this right angle triangle, we can write two equations, one for P and the other one for Q. Right? We have magnitude of S on the third side, VRMS times IRMS. And so we can write equations for P and Q using that power triangle. P would be VI times cos theta. Q is VI times sin theta, where V and I are both the RMS values of the voltage and the current. Okay. Theta, of course, is the power angle. And it is the difference in phase between the voltage and the current. Theta V minus theta I. The same as the impedance angle. The impedance angle also is theta V minus theta I. Right? No difference. Now, keep in mind, when you're trying to find P and Q, this equation refers to that single component. Okay? So if you're talking about a resistor, you can find the power for a resistor using this equation, but you would need the voltage, the current, and the phase angle for that resistor. Make sense? For a resistor, what is theta? Theta is the phase difference between voltage and current, but a resistor does not have any phase difference. Current and voltage for a resistor is always in phase, so it's cos 0. So for a resistor, power should be V times I. That's it, right? V times I. That's what we have learned. So we take the RMS values and we can solve for the power P as well as Q. The most common application of this would be for a source, because a source is supplying a voltage or a current, voltage and current to an entire system. That system would have a resistor, inductor, capacitor, right? And so if it does have that, the source will have an angle that is completely different from the components. And so that is where these equations will be very helpful. But again, we'll solve two problems and we'll see how we can actually use those equations as well as these to solve for the power quantities. These two equations, I squared times R, are basically the same equations that we used in chapters 1 and 2. And this equation right here on the left and right side is V squared over R. So I squared times R and V squared over R. Real power, P, so I square, of course, the RMS values times R, because it has to do with the resistance. The reactive power Q has to do with the reactance, so that R is substituted with an X. And that X represents the reactance of either that inductor or that capacitor. Okay, the form of the equation is exactly the same. No other difference. Except now it is reactance X. Note when you use these quantities, right? Q by itself and X by itself does not have J. It does not have the imaginary number. It's just talking about that component, reactive power and reactance. It's when you take the reactance and plug it into the equation for impedance, you have JX, JXL, JXC. Same way, when you take Q and you plug it into the equation for S, total complex power, you would have plus JQ or minus JQ. By itself, it does not have a plus or, it does not have the imaginary number. So if there's ever a question and you're trying to find Q, make sure you do not include J in there. All right. Also, capacitor, we said capacitor is negative, right? In real life, power is never positive or negative. We simply say the system has 500 watts of power or 500 VAR or 1000 VAR. It's never plus or minus. Plus or minus is to indicate whether the energy is flowing in or out and the phase difference, right? And so QL would be plus, QC would be minus, just for us to balance out the equations. So let's look at example 1. Example 1 asks us to find the power for every component. I have 16 minutes left. More likely than not, we'll go over time, maybe about 4 or 5 minutes. If you need to leave at 10 o'clock, it's absolutely fine. We have 3 components again, similar to the previous one. We have inductor, resistor, and capacitor. Draw the equivalent impedance diagram as a first step. Equivalent impedance diagram is right here. Then I can write out and note that Vs is a minus below and plus up top. Current always goes from minus to plus. So I, the overall current being supplied by that voltage supply, is going up top, going in the upwards direction, right? It's going through ZL. So the current I is common to Vs and to the impedance of the inductor. And then you have R and ZC in parallel. And each one of those, of course, is in parallel, so they share the same voltage. They share the same voltage. You have IR resistor current, IC capacitor current. Then I have 3 resistors in the circuit. Apply our resistive reduction techniques. I would first start at the farthest end away from the power supply. I would reduce R and ZC in parallel to ZRC. ZRC is R and ZC in parallel, and then that ZRC is in series with ZL. And thus my total ZEQ is ZL plus ZRC. Once you reduce it to one single equivalent impedance, apply Ohm's law, and you find the total current in the circuit. Make sense? Right? Same thing that we did in chapters 1 and 2. So let's begin our calculations. Is the process clear? Right? Now it's only the math. Compare it to the standard expression, and I would obtain Vm 10 volts, or magnitude of the voltage source is 10 volts. Phase angle is minus 90. So phasor for the source is 10 with a phase angle of minus 90. Omega is given as 1000 radians per second. I plug it into the equations for ZL and ZC. Again, do the same thing. J omega L, 1 over J omega C. I find the answers in both rectangular as well as polar coordinates. Magnitudes for both capacitor and inductor impedances are 100. Phase angles are plus 90 and minus 90. Okay, plus 90 and minus 90. These annotations are already there in the class notebook, so they're already available to you. Okay, in case you're trying to catch up, and if I'm going too fast, it's already there in the class notebook. So once I have ZL and ZC, I have all 3 quantities, R, ZL, and ZC. I find ZRC. ZRC is, well, 2 impedances in parallel. Combine them the same way you would combine resistances in parallel. So R times ZC divided by R plus ZC. I have to go through a few hoops to come to the final answer. This is where a programmable calculator helps out very much. Because if you have just polar quantities, you don't have to perform this conversion. right? R plus ZC is 100 minus J100. In order to perform this division, right, I need to divide R times ZC divided by R plus ZC. In order to perform that division, I need both the numerator and the denominator to be in polar coordinates, and hence that extra step. Again, you can directly go from here to here with a programmable calculator. And then again, at the same time, I'll also find the answer in rectangular coordinates. So that is ZRC. Now at this point, if I wanted to find the voltage across ZRC and ZL, I can again apply voltage division. Right? I would have two resistors, or rather two impedances in series. I can apply voltage division at this step to find VL and VRC. Make sense? Right? So similar to the previous one, you can apply voltage division, or you can find the total current I, which we might need for the source later on. So I would be VS over ZEQ. ZEQ, of course, is ZL plus ZRC. So 100 minus J100 minus J100 plus 50 minus J50. So total impedance ZEQ has a magnitude of 70.71 with a phase angle of 45. Find the total current, magnitude of 0.1414, phase angle minus 135. VR is the same as VC. So I times ZRC would give me VRC. Remember, R and C are in parallel. Right? So the voltage across one is the same as the voltage across the other. You find just one voltage, that's it. Easiest thing to do is use R, because R does not have a phase angle. I mean, easier as in like, like one less phase angle, that's all. So easy is relative. Anyway, VR is exactly equal to VC. So you simply take I times ZRC. The other way to find it is voltage division. So you apply VS into ZRC over ZEQ, and you get 10 with a phase angle of minus 180. If you applied Ohm's law, this I times ZRC will again refer to it for student practice. Okay. Again, it's a simple calculation. Simply take the value for I times the value for ZRC. You should get the same value. Any questions? Does the overall process make sense? Okay. All right, so that is VRC. Once we have the voltage, we can find the current by applying Ohm's law, VRC over R and VRC over ZC. Each one gives us the current for the capacitor. Now, why are we finding the current? We already have the voltage. We can take the voltage and find the power that way, right? The original question is find the power for every component. So to find the power for every component, we can use any one of the equations that we already have. You can find power by V square over R, or I square times R, or I square times X, V square over X. So if you already have the voltage across the resistor and the capacitor, which is VRC right here, you could simply divide that by the resistance and get power P, or you divide VRC by XC and you obtain your Q, or QC. Make sense? See what I'm saying? Again, these are all tools in your toolbox. It is up to you to determine which equation you want to use. So here I'm showing you how we can use voltage divided by the resistance to find X, but we can find the current if we needed to, and apply I square times R or I square times X, and you will still be obtain the same value as we see here. So on the left side, I have the voltage. On the right side, I have the current. In an exam, of course, I would not expect you to solve it both ways unless you have time and you want to verify your answer. But I'm showing both equations right there. So it's up to you on which equations you want to use. Unless current is asked, you have no need to find the current. Right? You already have the voltage. You can just use the left side equations and solve for the power. You do find the current, you can use these equations and find still the same, no difference. All right, questions? Any questions at all? Notice that when I apply the equations and I have X in there, I do not include the J. I do include the minus sign. Okay, I do include the minus sign. So QC is minus 100 in both cases. And so my, XC is minus 100 in both cases. So QC ends up being minus 0.5 VAR. All right, QL will be positive. QL will be positive. Real power P, of course, is to do with the resistor. So it's watts, 0.5 watts. Now, add up all of the power in that system. What do we get? S is equal to P plus JQ, right? That's the rectangular coordinates for the total complex power S. Real power P is 0.5. Reactive power is plus J1 and minus J.5. This is QL. 1 is QL. And the minus 0.5 is QC. So QL and QC, right, from here. And you get total power is 0.5 plus J.5 VA, volt ampere. Your overall inductive requirement was 1 VAR, but because the capacitor is supplying half of that, the source only has to supply plus 0.5, not the total 1 VAR. Okay, the source only has to supply plus 0.5 VAR because the capacitor is supplying the other half. If you increase the value of the capacitor, this minus 0.5 VAR will go up in value. So it might become minus 0.6, minus 0.7, minus 0.8, thereby further reducing the requirement for Q from the source. Right? Your inductor requires 1, your capacitor is supplying 0.5 or 0.6 or 0.7 or 0.8. And that is power factor correction. Because without the capacitor, the source would have to supply 1 VAR, meaning it's a high reactive power, means Q is large. So if Q is large, the angle is large. I apply capacitor in the opposite direction, and so my angle is now reduced. Make sense? Right? The other alternate equations. The other alternate equation that we can use is this. So remember, I said we have the power triangles and we have VI cos theta, VI sin theta. So if we take the source, we already found the total current in the system, right? We already found the total current in the system. So this is going back to the point where we found I, total current I. Okay, so if we find total current I, which would be from this step, right here. So let me mark this point. We can go to alternate equation. I don't know what's up with the system. alternate equation, which is right here. And so once you have the total current I can find the phase difference between the voltage and the current. That would give me the power angle for the source, which is 45. Then I apply the equations Vrms, Irms times cosine of theta and Vrms, Irms times sine theta. And I can get directly the total value that is being supplied by the source. So the total real power being supplied by the sources comes out to be 0.5 watts. Total real power supplied by the source or reactive power supplied by the source comes out to plus 0.5 VAR. S in rectangular coordinates is plus 0.5 plus j 0.5 VA. If I equate this here, I already know my real power is P, reactive power is Q. So a much shorter method, but same answer. Unless the question asks you to find the power for the inductor or the capacitor, there is no need to do everything else that we did above, right? If it's only asking you for the source, then there's no need to do all of this. You can simply go from the current, total current supplied by the source, apply these equations, and done. Make sense? Here is where I talk about QL. So QL was 1 VAR. This is 1, right? So P, of course, remains the same. It's 0.5 watts. It's 0.5 watts. QL was 1 VAR, so it goes up 1. QC is minus 0.5, comes down. So plus 1 and minus 0.5. And so this comes out to be plus 0.5. And hence, my angle is now reduced. That's power factor correction. Make sense? Right? One final method is this. You have a third equation that you can use. S is equal to half VI asterisk. That asterisk notes the complex conjugate of that quantity. Complex conjugate simply means you invert the sign of the complex quantity. If it is A plus JB, it becomes A minus JB. So let me write it out here. Complex quantity means system's frozen. Can't really scroll down here. So the asterisk notes the complex conjugate of the quantity. Complex conjugate simply means if it is A plus JB, it becomes A minus JB. Or if it is R with a phase angle theta, it becomes R with a phase angle of minus theta. And so use this equation. S is equal to half VI asterisk, and that V and I are both phasor forms. So the equation V and I are in phasor quantities. So even more of a shortcut or short method. So simply plug in the phasor for the voltage, phasor for the current. You flip the sign of the phase angle. So minus 135 becomes plus 135. Right? Total current I that we found here had an angle of minus 135. Minus 135. So the complex conjugate of that current is plus 135. And so total S is 0.70745. Convert it into rectangular form, meaning from polar coordinates to rectangular, and equate it to the standard expression P plus JQ. You get P as 0.5 and Q as plus 0.5. Exactly the same answer shown with 3 different methods, or not methods, but 3 different set of equations. Yes.
In the first method where you use, like it has XL and XC.
Uh-huh.
What do those represent?
So X is just the reactance.
Oh, yeah.
X is the reactance. So impedance ZL and ZC is JXL and JXC. So XL and XC is basically, effect mathematical representation would be the impedance without the imaginary number J,
Okay.
right? Impedance Z is R plus JXC. So X is the reactance, simply omega L and 1 over omega C. Or, with the and. So it doesn't have the sign in rectangular coordinates. It doesn't have the angle. There's no phase information in here. It's simply talking about the magnitude. But again, this is one set of equations where we use p square over r, v over x, or I square times x. Second set is right here, where you find it for the source. And the third is, of course, down here. Again, it's just for the source, but you're using the complex representation, phasor representation for V and I. And you have the same answer using 3 different sets of equations. So it's 10:04, end class here for today. There's one more example remaining. I will either, well, I'll decide what I want to do. I might either solve it in class next week, or I might post a video about it. All right. I will see you all on Friday. If you have any questions, I'll be in my office later. I'm also available on Zoom. If you need to see me on Zoom, simply send me an email and I will log on.
Thank you, Professor.
Uh-huh.